Hello and welcome. Volatile is a qualifier used with variable declaration. It instructs the compiler that the variable has possibility to be modified from outside the program being compiled, and no optimization is to be done around the variable. In this lesson, we shall look into the volatile keyword and discuss its effect on the compiled code. Let's understand it with an example. Here, I have a simple code to print the value of loop counter in hexadecimal on the serial channel. The loop is implemented using the for construct, and the variable index of type unsigned integer is used as loop counter. The loop runs for 5 times, prints the value of the index, and exits. I shall compile the code twice. First, the code is compiled with a variable index declared as a plain variable, that is, without the keyword volatile. Let's call this scenario 1. And second, the code is compiled with a variable index declared volatile. Let's call this scenario 2. The compilation is carried out with the debug flag -g and optimization flag -os in both the scenarios. The compilation is carried out with the debug flag -g and optimization flag -os in both the scenarios. Let's examine the disassembled code of the function main in both the scenarios and understand how and what compiler has done in the two scenarios. The first difference is the compiler has added instructions rcall and in at the beginning of the function main in scenario 2. But these instructions are missing in the scenario 1. The rcall instruction decrements the stack pointer by 2 and branches to the offset relative to the program counter. However, the offset is 0, hence there is no effective branch and program continue to execute the next instruction. And the 2 bytes allocated on the stack will be used for variable index. Then the instruction in loads the register pair R29 and R28 with the high and low bytes of stack pointer. Remember, the register pair is referred as register Y. The stack pointer is initialized to the highest SRAM address at the beginning of the program execution, which is 08FF for the Atmega 328 microcontroller. The decrement of stack pointer by 2 causes the stack pointer to point to the address 08FD, and the instructions in loads the address with the register Y. With these instructions, compiler has allocated 2 bytes on the stack frame of function main. However, these instructions are missing in the scenario 1, where the variable index is not declared with the keyword volatile. So, where is the variable index stored? The answer is in the subsequent instructions. The next set of instructions prepare the registers to pass the argument to function init_usart and call the function. The instruction set is exactly the same in both the scenarios and unaffected by the way the variable index is declared. The instructions following the for statement in scenario 1 is LDI, which loads the immediate values 0 and 1 to the register pair R29 and R28. But the value 1 is used to initialize the variable index in the for construct. It implies the compiler has used the register pair R29 and R28 to store the variable index. But in scenario 2, the instructions LDI loads the register pair R25 and R24 with immediate values 0 and 1 respectively. The register pair is then stored in the address pointed by Y plus 1 and Y plus 2 using the instruction std. The register pair R25 and R24 is again loaded with the values at the addresses y plus 1 and y plus 2 using the instructions LDD. In reference to the initialization of register Y, the addresses y plus 1 and y plus 2 refer to the addresses 08FE and 08FF on the program stack respectively. Then the instructions SBIW and BRCS follows. The instruction SBIW subtracts immediate value 6 from the register pair R25 and R24. The instruction BRCS tests the carry flag and branches relatively to the program counter if carry flag is set. These two instructions control the continuation of the for loop in scenario 2. There are 2 points to be noted. 1. In scenario 1, the variable index is stored in register pair R29 and R28, but in scenario 2, the variable index is stored in the stack frame. 2. In the scenario 2, stack addresses holding the value of variable index is read every time the variable index is referred in the program. The instructions highlighted have the same functionality in both the scenarios. These instructions prepare the registers to pass the arguments to the function _int to ASCII hex and call functions _int to ASCII hex, sprintS, sprintcr, and sprintnr. The functionalities of the functions are the same as discussed in the previous section. Let's examine the second set of instructions following the second for loop. In scenario 1, the register pair R29 and R28 is incremented by 1 using the instruction ADIW. Then the register pair is compared with the value 6 using the instruction CPI and CPC. The instruction BRNE tests the 0 flag and branches relatively to PC if 0 flag is set. These instructions control the execution of for loop in scenario 1. In scenario 2, the instructions LDD load the register pair R25 and R24 with the value pointed by the addresses y plus 2 and y plus 1. These addresses store the value of variable index. The instruction ADIW, that is add immediate to word, increment the register pair R25 and R24. Then RJump instruction, that is relative jump, branches the program execution to the start of the first for loop. In these instructions, whenever the variable index is referenced in scenario 2, it is loaded from the memory to the register and operated on. From the comparison, we observe the register used to manipulate a volatile variable is always refreshed with the value from the memory where it is stored. Despite of the same code in both the scenarios except the usage of volatile keyword, the assembly code generated is relatively lengthy in scenario 2. This implies the compiler refrains to optimize the code around the volatile variable even there is room for one. But what is the need to refresh the value every time? And isn't code optimization good for memory constrained embedded system? Since a volatile variable's value is always refreshed, it is used to refer the memory mapped register which has possibility of being modified outside the program in consideration. It is also used to declare the global variable used to pass information between the interrupt service routine and the main program. Let's understand why compiler optimization can be dangerous around a volatile variable with an example. The partial code snippet shown implements a communication mechanism. The data received is read by an interrupt service routine rx_isr, and the function process_data implemented in main program processes the data received. The end of data transmission is marked by the special character EORX. The interrupt service routine reads the EORX character and sets the variable end underscore rx to 1. The function process underscore data waits for the variable end underscore rx to be 1 before processing the received data. The expression in while loop checks if end underscore rx is 0 and makes the function wait. The wait continues until the end underscore rx is set to 1 by the interrupt service routine rx underscore isr. But with the optimization enabled, the compiler removes the code following the while loop, assuming it to be an infinite loop because the variable end underscore rx is initialized to 0 and never changes in the main program. This leads to incorrect code generation and program failure. The problem can be simply solved by declaring the variable end underscore rx as a volatile variable. It inhibits the compiler to remove the code following the while loop, thus generating the correct code. Similar scenario may also occur in multi-threaded application where shared variable is used to communicate information between application threads where variable is modified asynchronously. So, the usage of volatile variable is significant in embedded programming. The volatile keyword is used extensively in res underscore map.h header file where register definition for ATmega 328 microcontroller are placed. However, it must be used carefully and sparingly as it inhibits the code optimization resulting in bloated machine code. With this, I conclude this lesson and hope that you have clearly understood the volatile and its uses. Thank you and happy coding.